In this section of chapter 6, I would like to discuss about electromagnetic radiation and wave nature of energy. Here you're looking at electromagnetic radiation starting with radio wave, then microwave is the same microwave that we use for heating purposes, infrared, and then visible radiation. Visible radiation is really made up of red, orange, yellow, green, blue, indigo, violet, all this color combination. All these colors together give the appearance of white. So when it passes through prism, then they get separated according to their wavelengths, and that's when you see all different colors. Right before rain or right after rain, also water droplets in atmosphere can act as prism, and that's why we often see rainbow color. Next to visible would be ultraviolet, then X-ray and gamma ray. As you are going from left side to the right, wavelength is decreasing. Radio wave has the largest wavelength, and then microwave, and gamma ray has a very small wavelength. Frequency also increases along that same direction. So what we learn here is as wavelength decreases, frequency increases. Even though we have all these different types of radiations with different wavelengths and frequencies, but they have one property in common. They all move at the same speed, and that's called speed of light or velocity of light. Here we're calling it velocity of radiation, which is 3.00 times 10 to the power 8 meter per second, and that's fixed. Now you can see here how velocity is related to wavelength and frequency. So basically you multiply frequency by wavelength, then you get velocity. You can double check this. Frequency has the unit of actually number of wavelengths per second. So frequency has number per second. Let's check this. Nu lambda, that's pronounced as nu. So that's per second unit, number per second, number of wavelengths per second. And then lambda has the unit of meter. So what you have now here is meter per second. And we know that meter per second is nothing but velocity. And in this case, it's the velocity of radiation, and that's the same as velocity of light. Now, if you look at a wave, the distance from the peak of the wave to the equilibrium line is called amplitude. That's the maximum displacement that happens from that equilibrium line, which passes through the middle of these waves. And the wavelength is the distance between two similar points in successive waves. For example, this point and this point are identical points or similar points, so the distance between them would be a wavelength. Same is the case the bottom ones, bottom peak and the next bottom peak next to it, and the distance between them would be another wavelength. Now you can see here we can have different shapes of these waves, and that's what you're seeing now. In this slide you're looking at two different waves, one with a larger wavelength. The top one has a larger wavelength. You can see the distance between similar points is longer, and the bottom one has more wavelengths fitted within the same distance. Basically, if you think that that distance is covered per second, that means the first one would have only 1.5 wavelength, and the second one would have 1, this is 2, this is 3.5 wavelengths. So per second for the second one, there'd be more waves would be passing every second than the first one. So frequency of the second one is greater than frequency of the first one, and it matches what we mentioned before. The larger frequency means smaller wavelength, and smaller frequency means larger wavelength. Here you're looking at electromagnetic radiation Again, this is taken from the book, and they're showing you frequency values as well as wavelength values. So wavelengths are given in meter here, and frequencies are given number per second, number of wavelengths per second. And the velocity of light I already mentioned, which is same as velocity of radiation, is 3.00 times 10 to the power 8 meter per second. Now this shows you some of the conversion factors which we often need for solving problems. Angstrom, 1 angstrom is 10 to the negative 10 meter, and type of radiation would be X-ray. Then nanometer, 10 to the negative 9. Ultraviolet and visible has that kind of wavelengths. Then micrometer, 10 to the negative 6 for infrared. Millimeter, again infrared, so you can see wide variation in infrared. Centimeter would be 10 to the negative 2 meter, and then that's microwave. And TV and radio waves are the longest ones. Now let's go over a problem. Before I go over the problem, I should define what is continuous spectrum and line spectrum. Continuous spectrum means you can see all these different colors of radiation: red, orange, yellow, green, blue, indigo, violet. Then it will be called continuous spectrum. But most elements, when they're heated and then give off radiation, they would give you some of these colors, not all of them. And those are called line spectrum, and they're very characteristic of those elements. So now let's go over problem number 17, page 241. So I'm going over this problem, number 17, page 241. A question is asking, what is the frequency of radiation? So let's write down the question mark. What is the frequency of radiation? That is the wavelength of 10 micrometer. So wavelength, I'm using lambda, which is 10 micrometer. So don't forget that expression that we are going to use in this, in solving this problem would be C equals to frequency times wavelength. So now before I use it to get frequency value, so I think I can do math here. Frequency equal to C over lambda. Lambda is the wavelength. Now C is given, the value of C is 3.0. Let's write down that value so we know what kind of unit I need to have. 3.00 times 10 to the power 8 meter per second. So obviously lambda unit has to be changed from micrometer to just meter. And micro, you keep in mind, micro means 10 to the negative 6. So let's do the conversion here. Let's have a line here. So 10 micrometer, I'm going to change it to meter. Micrometer to meter. 1 micrometer. Now remember, micro, then put down 10 to the negative 6. So that's going to be the conversion. It should read like this: micrometer, 10 to the negative 6 meter. Quite often students write down 10 to the negative 6 at the bottom and 1 on the top. In order to avoid this kind of mistake, I ask you to read it like this: micrometer, so 10 to the negative 6 micro, and then meter. So that should check out. The micrometer would cancel out. So that gives you 10 to the negative 5 meter. Okay. Now we are going to use this in order to calculate frequency. So nu would be given by 3.00 times 10 to the power 8 meter per second, divide by, let's draw another line here, divide by 10 to the negative 5 meter. and that gives you 3.0 times 10 to the power 13 per second. That's the number of waves per second, which is same as inverse of second. Now in part B, I'm going to show you the setup. The same question number, part B, they're asking, what is the wavelength of the radiation that has a frequency of 5.50 times 10 to the power 14 per second? So again, in this case, they have given you the frequency. Frequency is 5.50 times 10 to the power 14. 10 to the power 14 per second. So that the frequency is given, and you're supposed to calculate the wavelength. So lambda with a question mark, and we're going to use the same expression, but now this is nu equals to c over lambda. From here I can write down lambda equals to c over frequency, and you can complete the rest. Plug in the numbers here. C equals to 3.00 times 10 to the power meter per second, and frequency is also given here, which is 5.50 times 10 to the power 14 per second. So this should give you the final answer. Well, per second would cancel out, so this should have the unit of meter. Now we are going to do problem number 17D. So 6.17D, and that's page 241. Brown LeMay Burston book, 12th edition. Now question is, what distance does electromagnetic radiation travel? The question is about distance. Let's use D for distance. So what distance does electromagnetic radiation travel in 50.0 microsecond? So time is 50.0 microsecond. And we already know the velocity of light, which is 3.00 times 10 to the power 8 meter per second. So make sure you write down 3.00 times 10 to the power 8 meter per second. And that's true for every radiation. No matter whether you're dealing with blue light, red light, X-ray, the velocity is going to be the same, which is also known as velocity of light. Okay, now in order to get the distance, you can use this dimensional analysis starting with the velocity. So I'm going to do that. 3.00 times 10 to the power 8 meter per second, that's the velocity. And in order to get meter, that's the distance, I need to multiply it by second. But the question gives me microsecond, which is 50. And let's do the conversion here. You can do it either separately or you can do it in one step. So let me do it in one step. 50.0 microsecond. Remember, I need to change microsecond to second. 1 microsecond, again, you should read it microsecond. Micro is 10 to the negative 6. That's 10 to the negative 6 second. So now you can cancel out some of these units. Let's see what is left after canceling all those units. Microsecond cancels out. Second per second cancels out. Now you have meter, and that's the distance unit, and that should be right. Okay, so I'm going to write down that value. That's equal to 1.50 times 10 to the power 4 meter. So this is the answer to this question.